right, welcome back everybody. So this is the second in our series on Introductory Econometrics. In this short video, we're going to be learning about ordinary least squares. Now throughout the presentation, you'll learn what that is, right? We'll discuss how we estimate regression equations with both single and multiple independent variable models, right? So we have one variable explaining y and several variables explaining y. We'll talk about how we evaluate the quality of a regression equation, right? We describe how we fit. I'll show you how to describe the overall fit of the estimated model, and finally we'll talk a little bit about the misuse of the idea of R-squared, which is going to be how we're going to evaluate the quality of our regression. Now, this presentation is going to be a little bit technical mathematically. That said, for mathophobes out there, you can do this, right? It's going to look a little scary for a while, but for sure you can do it. It's not crazy complicated. One last thing is in this lecture we'll really be sort of getting under the hood of how regression analysis works, right? So this is essentially to teach you the mechanics of what's going on. Back in the day, when I learned this stuff, we did all this stuff by hand, right? But you don't do that anymore because it's a lot of work and computers can do it instantly. But we need to learn how it works, right? Okay, so that's what we're doing here. We'll just take a minute to review some of the things that we learned in the last presentation. Up on the top here is we start off our work with a hypothesized relationship. In this case, we're saying that we expect that variations in y, or a dependent variable, can be explained by, in this case, a single independent variable, or x. Last time we used the idea that we could explain a person's height by understanding their weight, right? So height being the y variable or dependent variable, and weight being the x or independent variable. And then we also have an error term there on the end that we discussed in some depth last time. From this, we use regression analysis to estimate a relationship between those independent variable and the dependent variable. We notate that estimated relationships with the little hats over there. Y hat, okay? And that should be a lowercase I. It's a typo there, not an uppercase I next to the Y. Okay, so the method that we're going to be discussing today is called ordinary least squared, or OLS for short. And this is a technique that is going to calculate the estimated values for those betas so that the sum of squared residuals is minimized. Okay, so why do we start with OLS? Well, first of all, it's relatively easy to use, right? You can get up and running doing regression analysis with OLS pretty quickly and easily. Indeed, by the next lecture, lecture 3, I'll have you up and running and doing that. Okay, so you're thinking like, oh, when do we get that stuff? Okay, soon, right? Okay. The second reason is because it's sort of logical, right? There's a certain logic to the idea that we're going to estimate a relationship that sort of fits the data on a very surface sort of level well, right? The third, statistically speaking, OLS estimates have many useful characteristics. That is, they're sort of statistically tidy, if you will. That's pretty complicated why that is, but we'll be getting into that in a few weeks when we talk in more detail about the assumptions of the OLS model. Okay, so how does OLS go about doing this? When we use ordinary least squares as a method of regression analysis, how does it how does it estimate this relationship? How does it estimate the value of those betas, or the sensitivity of our independent variables to our dependent variables? Well, okay, let's start with a simple hypothesized relationship where we're going to say that the dependent variable is a function of just one independent variable, right? So that we're going to say, like our height and weight example from last time. What OLS does then is it's going to estimate beta 1, right, the way we see over here, using the equation over here. And I apologize, between yi and y bar I, or y bar there, it should be a minus sign, not that I tried, I don't know, something's with the PowerPoint's equation editor that they won't let me make that a minus sign, but that should be a minus sign. So I'm just going to bring the mouse in here for just a second. That there should be a minus sign, okay? Otherwise, what are we saying here? Okay, we're saying the sum of all observations, xi, so the observed value of x, minus what? X bar is the mean value of x. So when we look at all the x values, so in this case it would be all the weights, right? Continuing from the example of last time, and we take the mean value, so we sum them all and divide by the number of observations, right? Get x bar. We're going to take that variation between those two, we're going to multiply it by similar yi observed values of y minus the mean value of y, okay, y bar, and we're going to take that sum of all those differences over what? Over the observed values of the sum of the observed values of xi minus the mean value of x. So these are the same, right? Okay, squared. Okay, so well okay, so that's how we're doing that, right? And then we're going to estimate the value of beta 0, right? So this intercept term here. Again, I know I've said more on that later twice last time, and now here again, right? But and from the estimate of that, right, we're going to take the mean value of y minus the estimated value of beta 1 times the mean value of x to derive our intercept. And in doing so, what we're end up doing is we're sort of fitting a line to the data, right? We're fitting a relationship to the data. Okay, so over there we have a diagrammatic representation of what we're talking about. The small blue circles represent observed data. So weight in terms of height, right? So we've got a variety of little blue dots here. I'm going to use the mouse, right? One observed point, two observed point. And what our OLS regression is attempting to do is to fit a line that estimates a relationship between weight and height based upon the data in a specific way. Okay, what specific way? What our OLS regression is doing is attempting to minimize the distance between the the squared of the observed data and the estimated regression line. The observed data and the estimated regression line. Observed data, so on. For all of these. So if we were to sum up the distances from these observations to the regression line, square it. Okay. What OLS is doing is minimizing that distance. Okay, minimizing that distance. So in that sense, this line is the best fit representation using OLS for this set of data relating height and weight. Okay, so try to keep that image in your mind of sort of this balancing act that OLS is doing to match this observed data to an estimated regression line. Okay, now the slope of this is what, right? You guessed it, right? That's your beta 1, right, in this case. Okay, so here we are, multivariate regression, right? Okay, so now we have multiple variables. Okay, so right over there we see a hypothesized relationship between two independent variables, x1 and x2, and a dependent variable, y. Okay, so if we to continue our analogy of height and weight, maybe we're going to say, okay, well, our new hypothesis is that people's weight goes up people's height goes up as their weight changes, but also people's height goes up based upon nutrition or something like that. Okay, so x1 is maybe weight, right, and then x2 is maybe nutrition or something to that effect, right? Well, if we run an OLS regression, the estimates of beta 1 and 2 are going to be calculated similar to how it was calculated with a single variable regression equation, but we have to do a little more work. So on the bottom there, you see the mathematical representation of how we would estimate beta hat 1, or beta 1. I guess the hat is redundant when we say estimate. Now, one note about the notation there. Okay, so you see a bunch of small y's and small x's. Okay, small y is the variation of the observed y from the mean y, or y sub I minus the mean of y, or y bar. Okay, similarly, the small x is observed x's difference from the mean value of x. Okay, and then of course the summation notation there is the same as it always is. Okay, so those lowercase y's and x's are actually summaries of more stuff that's embedded in there, right? So if we were to write that all out, it would be quite a bit longer still. Okay, but I want you to keep in mind what it's doing. It's doing the same thing as it is in the single variable regression equation. Now, to estimate beta 2, we essentially do the same thing, except for all the lowercase 1's are going to change to 2's, and all the lowercase 1's, or 2's, excuse me, are going to change to 1's, right? And so that's how you do this. Now, if you're thinking like, oh my gosh, okay, well, this is what the software does, right? For 1 or 2 variables, even 3 variables, the math isn't too bad, but when you get up to, many more variables, you're talking a lot of plugging and chugging in terms of mathematics. And just be glad, we have these packages. I mean, back in the dark ages when I learned all the stuff of the early 1990s, we did this stuff by hand, right? You'd never do more than three variables, but that's how you did it, right? So if you want to do it by hand, the textbook for this course has a nice exercise you can work through in this. It's in the chapter for this. It's in chapter 2, and it's really not as bad as it seems, honestly. So now that we understand what OLS is doing and a little bit of how it works mathematically, it's important that we start to talk about how we understand the quality of the work that we've done, or the quality of the estimated regression output. And we do that with these terms over here. Okay, total, explained, and residual sum of squares. These, again, the mathematics looks kind of scary, but it's not. Okay, you say no, yes it is. Okay, no, just hear me out. All right. So the first of these is the idea is the total sum of squares, right? And what this is the variation from the actual observations, so yi, right, and then the mean value of y, summed across all observations and squared. Okay. In the case of OLS, we can break this TSS idea down into an ESS and an RSS, which stands for explained sum of squares and residual sum of squares, respectively. Okay, and again, there's the math associated with that. So we can see the first chunk there. This chunk here, right, is our ESS, okay, and this chunk here is our RSS, okay, so residuals, right, explained. So in this chunk here, what are we talking about? We're talking about the variations in y, so our estimated values of y and our mean values of y, that is the variations from the mean, okay, so this is our explained sum of squares, and this is our residual sum of squares here. Okay, so OLS as a statistical technique is essentially what it does, right, is it minimizes RSS relative to TSS. Okay, so it's minimizing the residual component relative to the total. We should understand that when we're doing this work, we have to sort of take a step back at all stages of our work, when we're developing the hypothesis, before we run our regression, as well as after we run our regression. We need to really carefully think about does our hypothesized relationship make sense from the standpoint of economic theory? We need to think about, well, what do I mean by that? Okay, well, like if we have a result that says that when prices go up, people buy more, right? So that'd be a sort of upward sloping demand idea, right? It's not necessarily wrong, right? It's not necessarily wrong, but we need to scrutinize that a lot more we need to give that idea a lot more scrutiny than the opposite result, that when prices go up, people buy less of a thing. Okay, and this happens, right? This happens in our work. We'll talk about that when you start doing this work, and you're going to get some unusual results, and we'll talk about that. Does the regression fit the data? Okay, well, we're going to talk about how we find it out in just a second. What is the quality of the data set? Well, bad data makes for bad results. Junk in, junk out. If your data set's composed of asking your family a few questions, your regression results aren't going to be very good. Okay. Does OLS make sense to use, right? So the assumptions of OLS. We're going to cover this in a couple chapters from now. In most cases, OLS makes sense, right? But there are some situations where it's totally inappropriate. Okay. Are the variables that are used sound, right? This is a problem that we can have in a lot of work, is we end up with these sort of spurious correlations, right? So let's imagine that, every time I put a hat on, the data shows that dogs bark more often in the neighborhood. Well, are the dogs barking more because I put hats on? Well, we noticed that those two variables track together. Probably not, right? When we develop these models, right, we want to be thinking about what types of variables to employ, because there is such a thing as having too few variables, obviously, but there's also a thing such as having too many variables, right? We'll talk about how we analyze that going forward, but at this point we want to just be thinking like, does this even make sense what we're doing here? And we want to think really carefully about that. Finally, we want to be thinking, does the regression output appear to have any major flaws? Like, I mentioned prices and quantities a little earlier. One thing that we found a few years back when we were doing some work on bike paths and like home prices, we found that when you put more bike paths into a city, that home prices actually fell, right? And like this is like, people love bike paths, right? So like, oh my gosh, this is a problem, right? And of course, that was both wrong and right, as we later found out. We had to scrutinize that result because it didn't really make sense. And it turned out when we poked a little more and we refined our work, we found out is that some type of bike paths raise home prices and other types of bike paths lower home prices. Particularly if you put a bike path in somebody's backyard, home price goes down. Okay, so again, what we were talking about last time, this is a process. Right? This is a process of continual refinement, and we need to be thinking that way at all times about the work that we're doing. All right, now sort of the you might say, okay, well, what was our quick thing, right? Okay, well, the quick thing that we sort of talk about when we talk about how the quality of regression output is R-squared. And R-squared is this relationship over there, or the ratio of explained sum of squares to total sum of squares. Okay, so what that is it's a measure. If you go back, go think like, okay, go back through all the stuff we've talked about in this class. Essentially, that is a measure of how good of a fit the regression line is. So it's telling us how much of the movement in the dependent variable can be explained by our independent variables. Okay. Now, of course, that's bounded by 0 and 1. 0 meaning like our independent variables don't explain anything about the movement in y. Okay, and 1 on the high end would mean that our independent variables explain everything about the movement of y. Now, virtually always you're going to be somewhere in between that. There's going to be things that you're able to explain, or at least that R-squared is telling you're explaining, and other things that you're not able to explain. Moving on, right? Problem with R-squared, and you can kind of see this in the formula for it, right, is that you can always increase your R-squared by adding variables, right? Because TSS, total sum of squares, is variation in y, and that's not going to change as you add more independent variables, but your explained sum of squares is going to continually go up, right? So that ratio is going to continually increase as you add more variables. So we have this idea of adjusted R-squared, which we note as R-squared with a bar on top over here. You see it over there, okay? And it looks like this. Now, there's a couple new variables in there, right? So that you've not seen before. Everything else like y's and summation signs, it's all same as before. N is your number of observations. Okay, K is your number of independent variables, coefficients. Okay, so when we consider that, right, we see in this that what adjusted R squared is essentially doing is giving us a sort of cost benefit of adding additional variables. Right? So if we add more variables to our model and it causes R squared to go up, but not adjusted R squared, our adjusted R squared is telling us that, you know, those variables aren't really helping us out at all. They're not helping us, this model, to improve. So if we notice that R squared is going up, but adjusted R squared is staying the same, again, tells us the quality of the variables we're adding are not really very good. And of course, adjusted R squared could even go down when R squared goes up, right? If you're really not adding good variables. Okay, so we do have a way of sort of thinking about whether we should be adding more variables or should not be adding more variables. So more variables, not necessarily good. Doesn't necessarily make for better models. It doesn't necessarily make for superior explanations. Increasing R squared doesn't necessarily mean that you've designed a better model or run a better regression, or that you're explaining more, because that possibility for spurious correlation always exists. Right? But we always need to safeguard against these spurious correlations, right? So this idea that, well, I put my hat on and so now dogs are barking more, or something like that. Or all right, so that's the end of this presentation. Right, next time, you see here, we're going to be learning how to use regression analysis. So this time was all about the sort of theory and the mechanics of what's going on inside an OLS regression. Next time we're going to dig in and start doing that. Okay, so I hope you'll join me for that. I'm pretty amped about that. We'll see you then. Take care. Bye.